Hi guys, so we did cover the vector equation of a line. So let's have a quick recap. So if you got a line, then you need one point on that line, and you need the direction vector as well. And also you need the t, which is the scale factor. Similarly, if you got a plan, so you have one extra dimension. So this time you need one point on the plan, and you need two direction vectors on the plan. These vectors are not unique. They could be any vectors on the plan. S and T are the scale factors. Okay, so let's have a look at this example. So if you got 3 points given to you, so you can pick A to be your reference point. So that will give you the vector R0. Now, you got three points, so you can find basically two vectors. So if you find vector AB and then vector AC, all right, so now use this formula here. So substitute in OA and then substitute in AB and AC, and that's how you find the vector equation of the plan. Okay, so normal vector to a plan. If you have two direction vectors on the plan, so we call them U and V. So to find the normal vector, so what you do is you take cross product between U and V. And if you need to find the unit vector, then you just divide it by the magnitude of the cross product between U and V. Okay, let's look at this example. The formulas are not hard to use, but you need to know how to identify the important information. So if you got a vector equation in a plan, so you need to be able to identify that these two are the direction vectors. So all you need to do now is take the cross product between them. And once you got that, so you take that vector n divided by the magnitude to get the unit vector. All right, so just like a line, for a plan, you can also find the Cartesian equation. So this is the important equation. What it's saying is that if you pick any position vector on the plan and then you dot with the normal vector, it always gives you a constant. It doesn't matter what point you pick, okay? And I think that's a very useful result. So the position vector R is given by xi plus yj plus zk. And if you let r0, so that is the basically the position vector of one point on the plan, and you just let this coordinate be x0, y0, z0, and you let the vector n to be given by ai plus bj plus ck. Okay, so if you want to convert this vector equation into the Cartesian equation, you just need to take the dot product. So take the dot product between r and n, you will get ix plus by plus cz. And then you take dot product between r0 and n, it will give you a constant d. Okay. All right, so this example, you have your r, which is the vector equation, and you want to work out a Cartesian equation. So you need R0. So you can pick this point here to be your R0. And then your vector n. So vector n can be found by taking the cross product between U and V. Okay, so that's how we find vector n. So once you got that, so you take R0 and then you dot with the vector n, and on the left hand side, so you take R and then you dot with vector n. So you just expand everything out. So you will end up with this equation. Okay, so how do we find the perpendicular distance between a point and a plane? So I would memorize this equation here rather than working everything out from scratch. So we want to find the shortest distance between point Q and the plane, and you let point P be a point on the plane such that the vector PQ is perpendicular to the plane. So the formula is very simple. So this distance is just a magnitude of the dot product between the vector PQ and the unit normal vector to the plane. Okay, let's see how the formula works here. So in this case, you are given this equation and you're given the point Q as well. So you want to find the shortest distance between Q and that plane. So firstly, so we need to work out the unit normal vector. Okay, so looking at the left hand side here, so the left hand side can be found by taking dot product between the position vector xi plus yj plus zk, and then you dot with the vector n. So that means the vector n got to be 2i minus 3j plus 6k, and the magnitude of this vector is 7. So to work out the normal unit vector here, so you divide it by the magnitude. Okay, now point P, so you pick basically a point that satisfies the equation above, and this point is not unique. Okay, so let's check. So so in this case here, to make things easier, if you let x to be 1 and then y to be 1 as well, so z will turn out to be 0. So this is the point that we want. And then we take the dot product between PQ and the normal unit vector, okay? And then you take the magnitude of it, and that is the shortest distance between the point Q and the plane. Alright guys, so this time we want a specific point. So this time we want the perpendicular distance between the origin and the plane, okay? So you let point P be the point on the plane, okay? So you have r dot n is equal to some constant. So the formula to work at a distance is just equal to that constant divided by the vector n, and then you take the magnitude of that. So the constant d is just the dot product between a position vector and the normal vector. Okay, so in this example, so you have that vector equation here, and we want to work out the distance from the plane to the origin. So as you can see from here, so this one is your vector n, and this one is the d. So it's very straightforward to apply the formula. So how about intersection between two planes? So we did cover intersection between two lines. So the concept is similar, okay? So in this case, you are given this equation, yeah? And then you want to work out the vector equation and line of intersection to between these two. So what you can do is you solve simultaneous equation. But in this case, we got two equations with three unknowns. So what you can do is you let one variable, so let's say z, you let z to be some value t, and then you work out y using that equation there, you work out y in terms of t. And similarly, you work out x in terms of t by substituting y and z into this equation. Alright, so now you got z equal to t, y equal 1 minus 5 over 7t, x equal 3 plus t over 7. Now you substitute these 3 back into the position vector. And that is your equation. Keep in mind that this bit here, you see there's a fraction of 1 over 7. T is just a scalar factor. So what you can do is you can also multiply this whole vector by 7, for example. Okay, last thing I want to cover is the angle formed between two planes. So if you think of it like this, yeah, so if you draw the two normal vector, so the angle formed between these normal vectors would just be the angle formed between the two planes. Alright, so let's look at this equation here. So from the first equation, you can work out n1. Hopefully by now it's clear enough. So the left hand side, you take dot product between r and n, and you get this. So that means n1 got to be 3i minus 4j plus k. Similarly for the second plane, so n2 would be this. And you have learned how to work out the angle formed between two vectors. So taking dot product, okay, that will give you cosine theta. The dot product between the normal unit vector, okay, so it will give you cos theta, and then you take cos inverse to work out the angle. For the second example, in this case you need to do a bit more work to find the normal vectors. So you are given the vector equation here of each plane. So you know that to work out a normal vector, you take the cross product between the two direction vectors. Okay, so you do that for R1 and then you do that for R2 as well. And once you got N1 and N2, so you can find the unit vectors and then take the dot product between them. That will give you cosine theta. And then take cos inverse to get your angle.